GATE examination. I'm very sure about that. Okay. So kindly cooperate while taking in the class. Whatever the doubt without any hesitation, you can ask me, you can interrupt me at any time. And while attending the class, you have to take note of everything what is present in the presentation. So I request you all, you have to bring the notebook and pen when attending the class. Do you have the pen and paper with you? If so, I will start. In the chat box, you can give your reply. Do you have pen and paper with you?
Students, please be interactive. Please respond to the message in chat box.
Yes, Arul Karthik has responded. Thank you, Arul Karthik. Okay, I'm expecting you all have a pen and paper with you, because while taking the class, you have to solve the problem also. So this is completely the problematic. So you have to think of and you have to answer. Okay. So let
Ma'am,
us
please,
start.
please
Yes,
share your screen, ma'am.
yes.
Okay.
I will start my presentation. Is the screen is visible?
Yes, ma'am. Yes, ma'am.
So myself, Callens Christiana. I'm heading the Department of Computer Science and Engineering, State Institute of Technology. So today I'm going to take a class on theory of computation. And these are the books I referred for preparing the material. And kindly you can take a note of this also. So the blue color text is very important. Okay. So you can learn the main concept from this Ullman book, and the other three are the additional. So you can take a copy of this so that you can refer anything from this book. This will be very helpful to you. So we start with what is theory of computation. Theory of computation is a branch. It is not a branch of the, not only the branch of the computer science, it is the branch of even mathematics also. It is a branch of computer science and mathematics which deals with how efficiently the problem can be solved on the model of computation. So model of computation is nothing but a mathematical model. Okay, so there are which is represented by some mission structure. Okay, and these mathematical models are solving the problem with the help of the algorithm. Definitely you know what is algorithm. Okay, so we have to see what is model of computation and algorithm. Model of computation is nothing but which just describes the set of allowable operation used in the computation and their respective cost. So definitely with respect to the model, we have to pay the different cost. The problem can be solved with the help of the different models. There are different model of computation is there. The same problem can be solved with the help of more than one model, but the cost we have to pay is different. The cost is here means that the computational cost. Okay, and you know how the computational cost is calculated. And algorithm is nothing but, you know, the algorithm is a way to solve any problem. And these are the three areas of the theory of computation. One is automata theory and language. And this class, we are mostly concentrate on the automata theory and languages, and computability theory and complexity theory. So while you are referring the GATE question, so with respect to these three fields, you can expect more questions from the first field, that is called as the automata theory and languages. And you can give the least importance to the computability theory and complexity theory in theory of computation. The automata theory is nothing but it is a study of abstract computational devices. We are going to study the different abstract computational devices. These devices are called as the models of real computation. So what do you mean by computation? Anything is called as the computation. For example, if you are adding two numbers, that is also called as the computation. I want to check whether the string is having the balanced parenthesis or not. That is also called as the computation. Okay. So anything is called as computation. Computation is nothing but any operation. So for that operation, if you try the solution with the help of the computational devices, all are called as the computations. Okay, so how the computation can be happened? That can be represented with the help of the abstract device. Do you understand? The study of such abstract devices is called as the automata theory. Okay, and language is nothing but these are all the strings which is recognized by the automata. The language has the member as strings which is recognized by the automata. And other areas are computability theory and complexity theory. The computability theory is nothing but it gives the answer for the question at what extent the problem can be solved by a computer. We cannot have the guarantee that all the problems are solved by the computer. And you know, the algorithmic notations, definitely there are some problems which cannot be solved by the computer. And we called such problems are non-deterministic problem. Okay, I think you are familiar with NP complete and NP hard. Okay, some problems that cannot be solved by a computer in a finite amount of time. Okay, so the computability theory, okay, that gives the question, that gives the answer for the question that at what extent the problem can be solved by a computer. We cannot give the guarantee that all the problems are solved by the computer. And complexity theory, in the sense, the complexity theory consider not only how the problem is solved, but it also consider how efficiently the problem is solved. Okay, so efficiency is measured by means of two aspects. One is called as the time complexity and other is called as the space complexity. And time complexity is nothing but how many steps is required in order to get the result of the computation. And space complexity is nothing but it tells how much space is required in order to perform the particular computation. That is called as the space complexity. And the computability theory and complexity theory is also the branch of the theory of computation, but we have to give the more focus to the automata theory and languages. Automata theory is what? Automata theory is nothing but a study of abstract computational devices. Okay, so computational devices is nothing but it gives a picture of the model of the computation. So we have to see what is model of computation, how the model of computation is represented with the help of the different model. That will be the scope of the automata theory and language. And this is the model of computation. It is the if the screen is visible, the screen is visible to you. Are you getting the matter very clearly? Anyone kindly respond? Arul Karthik?
Yes, ma'am. Visible, ma'am.
Okay, thank you, Pa. So this is the widely accepted model of computation. So in order to do any computation, these two parts is very important in computer. One is called as the CPU and other is called as the memory. Okay, why CPU is important? Because it actually performs all the computations and calculations. And memory, why memory is important? Because we have to store the data in a memory. Okay, so once we have the storage, then only we can retrieve the data and perform all the calculation, and the result of the computation is stored back into a memory. Okay, so this is the general model of the computation. We require the CPU and memory, and the different components of the computation. Different components of the computation, what are all needed in addition to the CPU and the memory. Memory again classified into temporary memory and program memory. So temporary memory is nothing but in that memory we can store all the data. Program memory, all the instruction, how the particular operation has to be performed, that is stored in the program memory. And input and output, these are additional. Okay, so you have to give the input to the CPU, it will perform all the operation and it will give the output. We can receive the output through the output devices. Okay, for example, we consider the computation. Okay, we need to perform f of x is equal to x is cube. Okay, the computation is x is cube. Whatever the value we are giving, your system has to perform the cubic value of such. Did you understand? Okay. So in a program memory, we have to write the instruction how the x cube can be computed. Okay. So if I give the value 5, how the 5 cube value is computed. Your CPU cannot perform all the operations simultaneously. The CPU can capable of performing the single operation at a time as a theoretical matter. So the x cube, how the x cube can be performed, you have to give the steps to the CPU that once the x is received, you have to first compute the value of x into x, that is x squared. And that result is called as a temporary result. You hold the temporary result x square, and that x square is multiplied with again x, that will bring the result of x cube. In such a way, you have to give the instruction to the CPU. So those instructions are stored in the program memory. Okay. So we called this is the pseudocode of such x cube. Okay. So this is the instruction actually. First, we have to compute x into x, that which is nothing but x square. Then the x squared value will be multiplied with x in order to give the result of x cube. Okay, this is stored in the program memory. If suppose I am giving the value x is equal to 2 as input, okay, in temporary memory, actually calculation is carried over. That is 2 into 2. That will give the result of 4, and that is stored in the temporary variable z. And that z is actually the x square value, and that is again multiplied with x. What is x now? 2. And x squared into x, that will give the result of x cube, which is nothing but 8, and that will be printed as the output. We are getting the value output f of x as 8 through the output device. So this is these are the components required for the computation. With the help of this component, we can define what is automaton. Okay, the components required for the computation as a whole is called as the automaton. Because what is automaton? Automaton is a model of a computation. Okay, and we know what are the things is required for the computation. Okay, input is required. Okay, the input is received by your processing device, and that should be a program memory. Why program memory is required? Because it gives how the computation can be performed. The algorithmic part is stored in the program memory, which will give how the computation is performed. Why we need a temporary memory? Because your CPU cannot perform the whole computation at a single step. It has to do a computation step-by-step manner. Okay, how the computation can be performed with respect to the input in a step-by-step manner is illustrated in a temporary memory. Oh, so these are all the components required in order to perform the computation. So this is called as the automation. Automation is nothing but a model, and very importantly, which is required? The computation, in order to perform the computation, the CPU and program memory. Why program memory is very essential? Because which will give how the computation can be performed. The part, the CPU and the program memory combined together is called as the automation. Because processing is very important, and how the processing has to be carried out is very important. Okay, the combination of CPU and program memory is called as the automaton. Okay, and we can represent the automaton as a different format. The CPU and program memory is represented by means of the states and transition in a model of computation or in a automaton model. Is it clear? Actually, this is our model of computation. We have program memory, CPU, temporary memory, input and output. Among the components, the CPU and program memory is very, very important. Okay, even without input also we can do operation. How? Instead of supplying a variable, we can imagine one value for the computation. Without receiving the input, we can do a computation. So input is also not at all necessary. Similar way, output. Okay. So instead of printing the output, the CPU itself hold the result. Okay. The output is also not at all important. Temporary memory. If your computation is very complex, you require the temporary memory. Otherwise, with respect to the statement given by the program memory, the CPU can automatically do the operation. So the very essential part is the CPU and program memory, because CPU performs the operation and program memory give the instruction how the operation is performed. So that important part we called as the automaton. Okay, so others are the auxiliary, input, output, and temporary memory are the auxiliary parts needed to do the computation, but the very essential parts are CPU and program memory. And in a model of computation, the CPU and program memory is represented by states and transition. Did you understand that? The circle represents the states and directed edge represents the transitions, and the states are connected by means of the transition. The entire thing we called as the automaton. Okay, you have to map this automaton to a real computer as the CPU and program memory combined together is called as the automaton in theory of computation. Okay, and this automaton is represented by means of the states and transition. The circle represents the states and directed edge represents the transitions. The other parts are the temporary memory, input, output. These are all the auxiliary to the any automaton. Okay, is it clear? Is it clear how we have to map the automaton to our actual computational device? And we have different types of automaton in theory of computation. And the three are very important. One is finite automata, another one is the push-down automata, and finally we have the Turing machine. Okay, so your syllabus is focused towards these three automaton: finite automata, push-down automata, and Turing machine. Okay, and these three automatas are differentiated with respect to how the temporary memory is configured, because this is, I'm saying that the computational model. Okay, you see this diagram, automaton, the temporary memory, input and output, these are all the auxiliary part. Okay, how the temporary memory is configured with respect to the complexity of the automaton model is differed. Okay, how the temporary memory is configured with respect to the complexity of automaton theory is varied. So in a finite automata, it has no temporary memory. It only has these states and transition, which is nothing but CPU and program memory as per your computational device. The finite automata has no temporary memory. The push-down automata has the temporary memory, but that temporary memory is configured by stack. Okay, and Turing machine is also has the temporary memory, and the temporary memory is configured by random access memory, RAM. Okay, so with respect to the temporary memory, how the temporary memory is configured, okay, that adds the power to the automated model. Okay, so with respect to these definition, can you tell which has more power? Finite automata or push-down automata, Turing machine? Anyone can answer. Which is more power? I'm giving the hint on the side note. The memory affects the computational part. More flexible memory results to the solution of more computational problem. Whenever you are automaton, okay, give the result of more problem, then those automatons will be very much powerful than other. Okay, so if your memory is so flexible, okay, if your memory is so flexible, kindly note the word, if your memory is so flexible, then the automata is having more power. Okay, with respect to that, which has more power, finite automata, push-down automata, or Turing machine? Anyone? So kindly make the interaction, then only I can understand you are following all the things. Which has more power? Anyone?
Students, please be interactive in the session. Please be active in chat box. Please respond to the question.
You can use your mic and tell. Maybe your answer is wrong. I will give the explanation why your answer is wrong. No problem, because this subject is new to you, I understand. I'm giving the explanation to you that whenever more flexible in memory, the device has more power. Okay, now you have, I am presenting you the three automata: finite automata, push-down automata, and Turing machine. Okay, I am saying you that whenever there is more flexible in memory, that automaton has more power. And finite automata has no temporary memory. Push-down automata in which the temporary memory is configured by stack concept. And Turing machine, which has random access memory. Okay. So with respect to that, which has more power? Anyone?
Finite, ma'am. Finite automate.
Finite automata has no memory. Then how do you say it is more power? I'm giving the hint to you. Whenever the memory is more flexible, okay, such automata has more power. The finite automata has no memory at all. Only limited amount of computation you can do if there is no memory. Then how do you say the finite automata is more power? Is it clear? The finite automata has the least power among the three. Then with respect to push-down automata, in which there is a memory is there, but memory is configured by means of stack. What is the restriction in stack? Anyone? I think you completed the class on data structures. What is the restriction in stack for accessing the data? Assume that your stack has 5 elements, 1, 2, 3, 4, 5. And the top pointer pointing the element 5. Okay? Are you following? The top pointer pointing the element 5. You assume that I want to access the element 3 from the stack. How can I access? How can I access? Assume your stack has 5 elements, 1, 2, 3, 4, 5. And the top pointer points the element 5. But I want to access the element 3. How can I access element 3? Is your stack paves the way to access the element 5? Once the top pointer pointing the element 5? Anyone? How we can access the element in stack? How you can access the element in stack? Anyone, please. Quick response I need. So you are attending the class with your classmates only. Even though your answer is wrong, there is no problem at all. This is for the discussion purpose only. If I am giving the lecture in one way, it will be very monotonous. There should be some interaction. How we can access the element in stack? Anyone? Anyone? Am I audible to you?
Yes, ma'am, it's audible.
But there is no response from your side.
Students, no problem. Wrong also you can respond. Ma'am
No
will correct
problem
it.
at all. There is no problem at all if you are saying a wrong answer. Okay, this is for the discussion purpose. Okay, so whatever the thing, okay, explained here, you can take it granted for your expansion of your knowledge only. So if your stack, I'm again saying the example, the stack consists of 5 elements, 1, 2, 3, 4, 5, and the top pointer points the element 5. Okay. May I access the element 3 if the top pointer points 5? Can I access?
Say yes or no.
Are you interested in the class? I think at least for that also say yes or no. Are you interested? Is the point is clear to you? Yes or no? Okay, I'm giving you the answer. So in stack, there is a restriction on accessing the element. We cannot access any element from the stack. Only the element which is pointed by the top pointer can be accessed. So I am posing you the question that the stack of 5 elements and the 5th element is, that is the element 5 is pointed by the top pointer. Only that element can be accessed. Other elements cannot be accessed. So in order to access the element 3, what you have to do? You have to pop. Pop means delete. You have to pop the element 5. Then the top pointer will decremented and pointing the element 4, and that element 4 will be popped off. Then the top pointer will be pointing the element 3. On that time only I can access 3. I cannot access any element from the stack at any point of time. That is the restriction in the stack. Okay, so with this restriction, the push down automator has not at all more power. Okay, sometimes it has more power than finite automata, but we cannot say the push down automata is superior. But when you compare the Turing machine, which has the random access memory, okay, from the name itself, you can understand that randomly you can access the data from the memory. Okay, so if you have the file pointer, you can move the file pointer either forward or backward. Okay, forward at any step, backward at any step, any data can be accessed. Okay, so here there is a flexibility of accessing the data. Okay, so whenever there is more flexible in accessing the data, the computational model is more powerful. Did you understand that? Okay, so you can make a note. I think this type of question may be asked. Okay, I will share some of the question to you at the end of the presentation. So based on that, you can understand even a single point will help you to understand the question and answering the question. Okay, so sometimes there may be the question may be like the hierarchy may be given to you, which is more powerful on what aspect. The question may be asked like that. So you can answer that the mathematical model, which is nothing but a finite automata and push-down automata and Turing machine. These are model of the computation. Model of computation is called as the mathematical model. The model of computations are powered by how flexible the memory is present in the respective model of computation. Finite automata has no memory, no temporary memory, so it has no power at all. It is the least power when compared to other model of computation, push-down automata and Turing machine. Push-down automata has an intermediate power of finite and Turing machine because it has the memory, but the memory with the restricted access. But Turing machine, random access memory, randomly you can access the data, so it has more power. Okay. So this is the representation of the finite automata, which has states and transition. There is no temporary memory, so it is crossed. Okay, and finite automata receives the input, which will produce the output. Okay, these are some of the practical examples where the finite automata is used. That is in elevators, in vending machines. Okay, so even though in ATM also, okay, so the ATM, how the ATM machine is dispensing the cash. So that is actually the real example of how the finite automata is working. And lexical analyzer is nothing but it is the one phase of compiler. Okay, so compiler, you know, it is a system software which is translating your high level language into a machine level language. The lexical analyzer is one part of the compiler which is designed with the help of the finite automata. So finite, these are the practical examples of the finite automata, even though it has a small computing power, and these are the examples of the finite automata. Okay, and push down automata, the states and transitions are there. In addition to that, the temporary memory, which is configured by stack. In stack, only two operations are allowed. One is push, another one is the pop. Push is nothing but we can insert any item over that. Okay, even though we cannot add the item in between that, at the top position we can insert the element. Similarly, from the top position we can remove the element. Okay, which is also receiving the input and producing the output. And the practical examples where the parser can be used means, so where the push automata is used mean it is used to design the parser for programming language. Parser is nothing but it is also the part of the compiler which is used for the translation purpose, the high level language into machine level language. And Turing machine, it has the highest computing power. And whatever today's model of computer, you know what is the advancement in the today's computer, that computer can be modeled by the Turing machine. Okay. And this is also the type of the 1 mark. Okay, which mathematical model can model the today's computer? You can answer that is the Turing machine, because here the memory is configured by random access. Okay, at any direction you can access whatever the data. Okay, with this flexibility it has more power. It is also receiving any input and output. Did you understand that? Okay, and example, okay, because it solved all the problem which is solved by the computer, so any algorithm is the example of this. Okay, so this is the comparison of power of the automata. Finite automata has less power. Push-down automata has the intermediate power, and Turing machine has more power. So with respect to its power, finite automata can solve only simple problem, and push-down automata can solve somewhat complex problem greater than the finite automata, and hardest problems are solved by the Turing machine. This is with respect to the model of computation. Is it clear to you with respect to the model of computation? Next, I have to go into the terminologies in the automata theory. Is it clear? How many model of computation we have covered so far? Anyone? So do not think me as an external person. I am presenting you for your clarification only. Okay. So this is for the benefit of you. So you have to use me at the maximum level in order to extract the knowledge. Am I pointing anybody? Kindly come voluntarily to answer. How many mathematical model we have discussed so far? You have the answer in the current slide. Kindly read it.
3, ma'am. 3.
3. What are they? Who is speaking? Who is speaking?
Arul Karthik, ma'am.
Oh, very good, Arul Karthik. Okay, 3. What are they?
Finite auto.
Yes,
finite automata,
push-down
automata, Turing machine.
And Turing machine. Okay, which is more power, Arul Karthik?
Turing machines, ma'am.
Turing machine. Why?
Turing machines because it's randomly access the data, ma'am.
Because of its memory. Okay, you have to say because of its memory, it has more power. Okay, because the memory of the Turing machine is configured by random access memory. Okay.
Okay.
Did you understand? Okay. Okay, thank you for your answer. So next, we move on to the basic terminologies, because whenever you know the terminologies, then only you can read the question. So some terminologies you have to very familiar. So for terminologies in automata theory, the first terminology you have to see about the alphabet. The alphabet is nothing but a finite non-empty set of symbols. Okay, alphabet is a finite non-empty set of symbols which is designated by the symbol sigma. You have to pronounce this is sigma. Okay, these are some of the examples of the alphabet. Okay, we have the binary alphabet. Binary alphabet, the sigma is denoted by 0 and 1. The symbols are enclosed by braces. So here the convention is very, very important. How we are using the parenthesis, how we are using the curly braces and bracket. All the thing has a separate meaning. So you should not use the some other brackets in place of the curly braces. The curly braces tells the set. Okay, whenever we have the set of elements, those elements are curved, closed within a curly braces. Okay, so this is a binary alphabet. The binary alphabet sigma is 0 and 1. There are two symbols of the binary alphabet. And lowercase letter, we can have A, B, C, D up to Z. And alphanumeric is nothing but alphabets and numerical. Okay, and you assume the numericals are the decimal numbers in the sense 0 to 9. These are the allowed characters. Alphabet is nothing but the permitted characters in order to frame the language is called as the alphabet. Okay, so whenever we are enter into studying of a new language, for example, you are very new to the English language. Initially, what you are studying, you thought about the alphabet. Once you're familiar about the alphabet, then you start how to frame the words. From the words only, you start to study how to frame sentence. After that only, you study how to frame a paragraph and all. Okay, this is a hierarchy, how you are learning the language. Likewise, in automata theory also, we have to see, okay, because initially I am saying that today's scope of the presentation is automata theory and language. Language here is nothing but any problem in computation is called as the language. Did you understand? Okay. The problem, whatever we have in a computation, is called as the language in the automata theory. Okay. In that word, we are called the problem. So, to study such language, we have to see what is alphabet. There are different alphabet is there. Alphabet is nothing but permitted characters in such any particular language. Okay. Binary alphabet means the two characters are allowed 0 and 1. Lowercase letters means A, B, C, D up to Z. Alphanumeric means A to Z. It may be a lowercase or a uppercase or 0 to 9. Okay. And engineering classes, the another example. So we can have 4 years of engineering classes. It may be first year, second year, third year, and final year. All the elements should be closed in curly braces. Okay. Next is nothing but a strings. String is nothing but a word. Okay. So it is a finite sequence of symbol chosen from sigma. Okay. The string is nothing but sequence of symbols which is chosen from sigma. I can say if my alphabet is binary, you assume that if my alphabet is binary, I can say 100 is a string because I can extract 1 and 0 2 times from the alphabet in order to frame the string 100. Is it clear? For example, after studying the ABCD in your English language, you can start to frame the words. Okay. So how you are framing the words? By drawing the alphabets from the English alphabet A to Z, you are start to frame the words. For example, if you are framing the word apple in the sense, you are extracting A from alphabet and P double time and L one time and E one time. Likewise, you are framing the word. So here also we can frame the string or word as a combination of the input alphabets. Did you understand? So for a binary alphabet, you assume that the 100 is a example string. Okay. And here, one important string you have to know, that is the empty string, which is denoted by epsilon, which is pronounced at epsilon. You see the symbol here. This is epsilon. Okay. Empty string is denoted by epsilon. Okay. And there are some sample string I am giving here. 001 is a example of the sample string. It is a binary string because it is framed by the binary alphabets. And A, B, C, D, this is the alphabet string because it is framed by the alphabet symbols. A1, B1, this is an example of alphanumeric string. Okay. Likewise, we can frame string of any length. That is also you have to understand. We can frame the string of any length. There is no restriction on the length of the string. You can frame the string of length 0, which is called as epsilon. Okay. Length of 0. No input symbol is there. Okay. Such string is called as epsilon. Length 1, we can frame the string. Length 2, we can frame the string. Length 3. Likewise, it goes. Okay. And the length of the string. Okay. So the length is nothing but a number. Okay. Length of the string is called as number, which is, for example, if your string is W, we can denote the length of the string as mod W. Okay. If your string X is having the symbol 010100, then mod of X is equal to 6. There are 6 symbols in that. Okay. If W, length of W equal to epsilon 0, then it is called as the empty string denoted by epsilon. Okay. And power of alphabet. This is very, very important concept. The power of an alphabet. Okay. In mathematics, we can have the power. Okay. In mathematics, we can have the power. And in case of the mathematics, if you have the value 2, what is the value of 2 power 0? So in mathematics, I'm having 2 power 0. What is the value of 2 power 0? 1.
1.
Okay. Similarly, 2 power 1. 2 power 1, you have 2. 2 power 2. 2 power 2. It means what? The 2 is multiplied with 2 again, which will bring the result of 4. Likewise, you can have, okay. Very similarly, here we have the power of an alphabet, okay. The power of an alphabet is different from the mathematical power in such a way that here power means how many times the respective symbol is repeated, okay. So power means how many times the respective symbol is repeated. In mathematical, you understand the power represents, okay, the multiplication of same value that amount of time. For example, 2 square in the sense 2 is multiplied by 2 times. 3 squared means that 3 is multiplied by 3 is multiplied by 2 times. Okay. And 4 squared is 4 is multiplied by 2 times. Okay. That power represents how many times the respective symbol is multiplied. Okay. That is the mathematical power. But here it is the power of an alphabet which says the power is nothing but how many times the respective symbol is repeated. For example, if you have the alphabet sigma equal to 0 and 1. Okay. I'm taking the alphabet sigma equal to 0 and 1. The screen is visible. Is the screen is visible to you? Say yes or no for this at least.
Yes, ma'am, it's visible.
Yes. Sigma power 0, I want to find out. Okay. So in automata theory, okay, the power means how many times the respective symbols is repeated. How many times the respective symbol is repeated. Okay. 0, sigma power 0. 0 times the symbol is repeated. What you are getting? 0 times the symbol is repeated. What you are getting? To assume that it is only 0, then it will be very clear to you. Sigma power 0, the respective symbol is repeated 0 times. It means what? 0 is repeated 0 times. Assume that this is nothing but 0 is repeated 0 times. 0 is repeated 0 times means it is what? Zero is what? It is nothing. Okay. The symbol 0 is repeated. Okay. No amount of time. That is the meaning. What is produced? What is produced?
Anything power 0, 1 upon 0
That is
power
the
0.
mathematical power. Do not confuse with the mathematical power with the alphabetical power. I'm here saying that here power means number of times the respective symbol is repeated. I am giving
0
you
times.
0 power 0. Upper 0 is repeated 0 times. 0 is repeated 0 times means what you are getting?
0.
Nothing you are getting. You should not say it is 0. Nothing you are getting. Okay. So nothing you are getting means it is nothing but a empty string. Okay. Empty string is denoted by what? Empty string is denoted by epsilon. Is it clear? Is it clear? Is it clear to you? 0 is repeated 0 times means nothing is nothing is produced. Okay, it is an empty set. The empty string is called as the epsilon. Okay. So this is very important. Sigma power 0 is epsilon. Similarly, sigma power 1, which is nothing but 0 power 1. Here power means what? Here power means what? How many times the respective symbol is? How many times the respective symbol is repeated? So 0 is repeated one time. So what string you are getting out of it? Zero is repeated one time. What string you are getting out of it? It is 0. One time the 0 is repeated, it is 0. Assume sigma power 2. Your sigma is 0. Okay. 2 times the 0 is repeated. What you are getting?
0, ma'am.
2 times you the symbol 0 is repeated. What you are getting?
0, ma'am.
0, 0. 2 times the symbol is repeated.
0, 0. Yes,
Yes?
ma'am.
Is it clear?
Yes, ma'am.
Okay. Sigma power 3. 0 power 3. Here power, okay, language power is nothing but how many times the respective is repeated. 0 power 3, what is it?
0, 0, 0.
Very good. Likewise, you can move. Okay. So here I'm having sigma as a 0. That is very simple alphabet I'm having. Okay. But in a practical case, the alphabet may have different amount of symbol. Okay. So in the presentation, I'm having sigma equal to 0 and 1. Okay. 0 and 1. You assume. Sigma equal to 0 and 1. You have to produce the sigma power 0, sigma power 1, sigma power 2, and sigma power 3. At least these you can have. Okay. Now you have to tell me what are the strings produced out of these. Sigma power 0 means what? Sigma power 0 means what? The symbols are repeated 0 amount of time. What will be produced? Anything power 0 here is epsilon. Kindly understand. This is very important. Anything power 0 is called as epsilon because power 0 means nothing is repeated. Okay. Nothing is repeated means the epsilon will be produced. This is the empty length string, 0 length string. We have the presentation. It is a empty length string, 0 length string. Okay. So here we have 0, 1, which will be produced one time. What is the string you are getting? Sigma power 1.
0, 1, ma'am.
Yes, very good. 0, 1. Okay. And here 0, 1 part 2. That is 0 and 1 is repeated 2 times. What are the strings you are getting? Anyone?
0, 1 and 0, 1.
No. Length 2. The power 1, power 2 says in length, the length of the string, length 2 strings you are producing in the combination of zeros and ones. You see the previous. Okay, 0 power 1 means the length 1 string is produced. 0 power 0 means length 0 string is produced. Length 0 string is called as epsilon. 0 power 2 means length 2 string is produced. 0 power 3 means length 3 string is produced. So here 0, 1, the whole power 1, the length 1 strings, they are 0 and 1 are produced. Both are length 1 strings. So here you have to produce length 2 strings. But in the combination of 0 and 1. What will be the result?
0, 0, 1, 1.
Very, very good. 0, 0,
1, 1.
1. Then what other combination of zeros and ones? First time
0,
it is 0, second time 1, or
1,
first time 1,
0.
second time 0. Okay, this
Yes,
is also the combination. So these are all the string. Did you understand? So how do you understand how many strings will be produced for any power? You can understand one simple formula, that is the number of symbols. Number of symbols in the alphabet for n. What is n? Number of times the respective is repeated. Kindly understand. So here the number of symbols are what? 2. 2 power 1 is equal to 2. 2 power 1 is equal to 2. 2 power 1 equal to 2. Is it clear? What is this 2 means? 2 is the number of input symbol in the alphabet. They are called as 0 and 1. Totally 2 symbols. And power 1. Here power 1 means 1 time. Okay. In length 1. Sigma power 1 we are producing. So how many strings you have to produce? 2 strings. So in the second one. So here. This is 2 power 2. 2 power 2 is equal to 4. Why 2 power 2? There are 2 input symbols. They are called as 0 and 1. Okay. And sigma square we are producing. Okay. In 2 occurrence we are producing. So total number of strings 4. So here 0, 1. The whole power 3. What will be produced? Anyone? How many strings you have to produce first? Tell me. How many strings you have to produce? See the formula I am giving on the right side. This I am highlighting by red color font. How many strings you have to produce first? This is all the basic. How many strings you can produce?
8, ma'am.
8, very good. Okay, because there are 2 input symbol and they are produced in length 3. Length 3 is called as a power. Okay, how many times the symbols are repeated is called as a power. That is the length. So 2 power 3 equal to 8. What are all those 8 strings? 0, 0, 0, 0, 0, 1, 0, 1, 0 in the combination of zeros and 1. That's all. Nothing else. 1, 0, 1, 1, 1, 0. 0, 1, 1, 1, 1, 1. So all the 8 comes. Is it clear? These are length 3 strings of zeros and ones combination. Here totally 2 power 3 equal to 8 strings is produced. Why 8 string? There are totally 3 input symbol and 2 power 3. 2 power 3 means 2 input symbol and in length 3, 2 power 3 equal to 8. Is it clear? Is it clear, Pa?
Yes, ma'am.
Okay. Now I am going to give one task to you. All these things I am copying. Now you have to tell me. My input is 0, 1, 2. So I'm here giving the restriction of the discussion up to the length 3. It may goes length 4, length 5, length 6. So it may goes up to infinite. Okay. Always epsilon power 0 is sigma power 0 is epsilon. Anything power 0 is epsilon always. Okay. There is no discussion at all. What is sigma power 1 here? Anyone? Sigma power 1. How many strings we can produce? Answer for me 2 questions. First question is how many strings we can produce? You apply the formula what I have given previous. See the right side. How many strings we can produce? Number of symbols, the whole power n. Here, how many number of symbols your input alphabet is having?
Number of symbols on the 3 தானே ma'am?
3 power 1?
3.
3. So what are all the strings produced?
3 strings.
3 strings. What are they?
0, 1, 2.
Very good. 0, 1, 2. That's all. That's all. Okay. The next sigma power 2. Okay. First you say how many strings can be produced? How many strings can be produced first? Total number of symbol is 3. 3 power 2. What is the value of 3 power 2? Three square.
9.
9. Okay, tell me those 9 strings of length 2 in the combination of 0, 1, 2. Anyone? Anyone? Length 2. The string length is 2, but they are in the combination of 0, 1, 2. What are they? I can write 0, 0, 0, 1, 0, 2. Then 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. The 9 strings comes. Is it okay? It is okay?
Yeah,
It is
ma'am.
okay to you? It is okay.
Yes, ma'am.
Yes. Likewise, you have to produce the next set. How many strings produced first? Tell me.
27, ma'am.
27. Very good. Because there are 3 symbols. 3 part 3 is 27. So you have to produce the 27 strings in the combination of 0, 1, 2. So only it is a combination of 0, 0, 0, 0. Every string should have a length 3. That is the restriction. So I can have 0, 1, 0, 0, what I can have 0, 1, 1, 0, 0, 1, 0, 0, 2, 2 I can have 0, 2, 0 I can have 0, 2, 2 I can have. Then start in 0. These are all the combination 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 2. Okay. These are all the string which start with 0. Okay. How many string I produced? 1, 2, 3, 4, 5, 6, 7. Okay. And 0, 2, 1, 0, 1, 2. Any other combination? 0, 2, 1 is produced. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Similarly, the string starts with 1. Okay. 1, 0, 0 I can produce. 1, 1, 0 I can produce. 1, 1, 1 I can produce. 1, 0, 1 I can produce. 1, 0, 2 I can produce. 1, 2, 0, 1, 2, 2, 1, 2, 1, 1, 1, 2. Likewise. Similarly, the string start with 2. Okay, 2, 0, 0, 2, 1, 0, 2, 1, 1, 2, 0, 1, 2, 0, 2, 2, 2, 0, 2, 2, 2, 2, 2, 1, 2, 1, 2. All 27 has come. All 27 has come. Anything is repeated? Kindly check. I think none of the strings are repeated. We have all possible combination of 0, 1, 2 in length 3. Is it clear to you? So likewise, you should have the capability of writing the strings. Okay, these are very first step. Definitely, you should know the capability because whenever I review the gate question, they are giving the language. Okay, they are expected that what are the strings produced by the language. Okay, later we will see. Okay, once you know the concept, then only you can go to the design of the mission. because they asked to design the mission by giving the language. Once you expanding the language, then only you can understand what are all the strings produced by the mission. Is it clear? At least somehow, by doing the practice, definitely you can get the idea. Okay. Do not get panic. By attending the single class, you can well versed in all the things. At least you understand the things. Have you copied all these things? Students? Students, is it clear? Is it clear, Pa? Shall I move on to the next? Are you there? I want to get a response from at least anybody, any one of you.
Yes, ma'am.
Yes, thank you. Okay, this is about the power of alphabet. Okay. So next is very important definition that is called as a Kleene closure, which is represented by star symbol. This is the operator. Okay. So in mathematics, we have the values. The values are applied in any operation. Okay. Then only we are getting the result. For example, 5 and 3, we have two numbers. By applying the multiplication over that, we are getting 15 as the result. 5 and 3 we are having, but applying the plus result, we are having the 8. Likewise, in languages also, there are the operator. One such operator is called as the closure. Okay. The closure is nothing but if you have the alphabet sigma, then the closure of the sigma is called as the sigma closure. Okay. The sigma closure is nothing but all combination of all length of strings. Okay. So it is nothing but sigma closure is equal to sigma power 0 union sigma power 1 union sigma power 2. This is the all possible length of all strings. That is called as a sigma closure. Okay. If you have your sigma equal to a comma b, only two symbol you are having, then your sigma closure will be epsilon. Epsilon is a zero length string. You know how to produce a zero length string. Okay. This is the zero length string, epsilon. Sigma closure. Sigma power 0 is a zero length string. Sigma power 1 is the one length. Likewise, okay, one length for a comma b is a and b alone. Two length for a and b is AA, AB, BB, BA. Okay. So sigma closure is equal to sigma power 0, sigma power 1, sigma power 2, sigma power 3, sigma power 4. Likewise, it goes. It is a infinite set. Okay. Sigma closure is a infinite set. Kindly understand. Okay. Because it is the union of all possible length of all strings. Do you understand? Okay. The next closure operator is called as the Kleene plus. It is a positive closure. It is read as positive closure, which is represented as sigma plus, which is the union of sigma power 1 union sigma power 2 union sigma power 3. Likewise, it goes. This is also the infinite set. It does not have the epsilon as a member, because here the first member start with the length 1. Okay, there is no sigma power 0 here. In previous case, Kleene closure, the sigma power 0 is also the member, but in case of the sigma plus, okay, in sigma plus, it starts from length 1 string, length 2, length 3, length 4. Likewise, it goes. It is also the infinite set. And the relation between sigma plus and sigma closure is when you subtracting, okay, epsilon from sigma closure, you are getting epsilon sigma plus. Okay, when you are subtracting epsilon from sigma closure, you are getting sigma plus. That is the relation between the sigma plus and sigma closure. You can note it down. This is also the very important relation frequently asked in the aptitude question. The relation between the positive closure and the Kleene closure. Okay. Sigma plus is equal to sigma closure minus epsilon, because the sigma plus won't have epsilon in it. Okay. Now I am going to give one fill up to you. Okay. Fill up. Okay. Here I am having that sigma star I am having equal to sigma plus Here I'm put a dash and gives so what operator you can fill in this dash? What operator you can fill in this dash? Anyone? There is an operator here. You see in the presentation. So here epsilon plus is represented in terms of epsilon closure. And there is an operator minus. The minus here is called as a set difference. Set difference because epsilon plus is also the set. Epsilon closure is also the set. And sigma plus and sigma closure is also the set. Epsilon is denoted inside a set. Okay. So this minus is called as a set difference. So here I am giving you the question. What is the operator you can fill? Anyone?
Minus
Based on the no. Here I'm giving the explanation about this sigma closure. Sigma closure is equal to this is actually the definition of sigma closure. I'm giving you the definition of sigma plus also. Sigma plus is equal to okay. See the difference? This is sigma star. This is sigma plus. Okay, I'm asking you the question. The sigma star is also the set. Sigma plus is also the set. Sigma star has the length of all the combination of the string. This is sigma power 0, sigma power 1, sigma power 2. And sigma plus is equal to sigma power 1 union sigma power 2 union sigma power 4. Okay. And what is the sigma power 0? What is the sigma power 0? Anyone? Sigma power 0 is?
epsilon.
Yes, this epsilon. Very good. You understand the point. Sigma power 0 is epsilon. That also you know. Okay. Now tell me which operator is applicable in the dash. You take this red color font expansion. Sigma star is here. Okay. This right side, sigma power plus is here. What is the sigma power plus? Sigma power plus is sigma power 1 union sigma power 2 union sigma power 3. Likewise, it goes. I'm highlighting this. This is called a sigma plus. Isn't it or not? Isn't it or not? What operator here you can fill? So you have right side sigma plus and epsilon separately. By doing which operation, you can get sigma closure. Students, by doing what operation you are getting sigma closure? I'm explain with example, then you can understand very clear. Your sigma equal to 1. You assume that. Okay. What is your sigma power 0? What is your sigma power 0? What is your sigma power 0?
Epsilon, ma'am.
Epsilon, very good. What is your sigma power 1?
0, ma'am.
0. Your sigma is 1. Your sigma is 1. That is your input.
Sigma, ma'am.
Sigma power 1 is what? Your sigma is 0. Sorry, 1. Which is nothing but 1. Which is repeated one amount of time. What symbol you are getting?
1.
1. Very good. Sigma power 1 is 1. Okay, what is your sigma power 2? What is your sigma power 2? Here power means what?
2.
2.
Power 2, then, ma'am.
Power is 2. Power in automata theory is what? How many times the symbol is repeated? How many times the symbol is repeated? I already given with the enough example. What you are getting? You apply 1 in place of sigma, the power 2. What you are getting?
1, 1.
Very good. 1 is repeated 2 times. That's all. Why there is a hesitation? Okay, 1 is repeated 2 times. Sigma power 3. Sigma power 3. 3 ones. Immediately how to tell. Okay, that's all. Okay, so now I'm writing sigma closure. Sigma closure I'm writing. Sigma closure is the union of sigma power 0, okay, sigma power 1, sigma power 2, and sigma power 3. Already we have in this definition. I'll copy this. Okay. Likewise it goes. So what is your, this is the set. Sigma power 0 is what? Sigma power 0 is epsilon. Sigma power 1 is 1 for our example. Sigma power 2 is 1, 1. Sigma power 3 is 1, 1, 1. Likewise, it goes, it is the infinite set. This is the value of sigma closure. What is sigma plus? That also you know. Sigma plus is nothing but sigma power 1 union, sigma power 2 union. That's all. According to our example, what is our sigma power 1? 1. Sigma power 2 is 1, 1. Sigma power 3 is 1, 1, 1. Sigma power 4 is 1, 1, 1. Likewise, it goes. Okay. Okay. Now just compare this. I'm asking this sigma closure. I'm asking you, what is sigma closure in terms of sigma plus? I'm here putting a dash to you. Then what is my question? Epsilon. This is my question. I'm asking you what operator I can here put in order to make this statement true. You just compare this. I'm highlighting this. You just compare the result of sigma closure and sigma plus. What you have to add in sigma plus in order to get sigma closure? What you are adding in order to get sigma closure in terms of sigma plus? I'm substituting this result also for your understanding. So here I'm having sigma plus. This is the sigma plus. Okay. Here I'm giving you a dash and giving you epsilon. What I have to make? What operator here I have to apply in order to get epsilon sigma closure? This is one set, that is another set. What operator I have to make in order to get a sigma closure? These are all the very basic, even 6th standard student can answer. This is very simple, like a set operations. Kindly share. Even it is a wrong, I will give an explanation to you. These are all the basic. Without knowing that, I cannot get into the mission design. You have to set, okay? In order to make them together, what operation you have to apply?
Union, ma'am.
Yes, that's all. Union. That's all. You have a two different set, okay? By taking the union, your answer will be, what is your answer? This will comprise of the epsilon. Epsilon is your zero length string, comma, and 1 length, 2 length, 3 length, 4 length, and goes. That's all. So the answer is the union. That's all. Okay. So I'm in the presentation, I'm giving you epsilon plus in terms of epsilon closure. Here I'm asking you the question epsilon closure in terms of the epsilon plus. So what you have to put in the fill-ups? That is the union. That's all. This is very similar to the set operation. Set union, set difference. That's all. Is it clear? Is it clear to you? So this is the relation of sigma plus in terms of the sigma star in terms of the sigma plus. Is it clear? Is it clear now? You are joining the two set. Joining is nothing but a union. Let us get into the next slide. The very important definition, the language. The language is called as the subset of sigma closure. Okay. So here you have to understand some set terminologies, set operations and membership. All the definition you have to know. Okay. In order to understand this concept. So a language here is the subset of sigma closure for some alphabet sigma. It can be finite or infinite. Can you understand? Sigma star is always infinite. That we know. Sigma star. Okay. Even sigma star, even sigma plus, all are infinite. We are putting dot, 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 and then we are close the brace. Okay. But what about the language? The language may be finite or infinite. Okay, we cannot certainly saying that it is a finite. We cannot certainly saying that it's infinite. Sometimes, with respect to the constraint, it can be finite or infinite. Okay, the language is denoted by the letter L, capital letter L. Okay, so always the set are denoted by the capital letter. Okay, you have to make the convention very clear. The set is denoted by the capital letter, and the member of the set is denoted by a lowercase letter. Okay, uppercase letter is used to denote the set, and lowercase letter denote the set element. Okay, and each string is called as a member of the language. The string is called as a member of the language. We can say collection of string is called as a language. Anyway, you can say. Okay, and very similar to the empty string, here also we can have empty language. Empty language is represented by null symbol. Okay, null, pi. Okay, the symbol null or pi, it is representing the empty language. Okay, and the empty language is not equivalent to empty string. Even your language having the empty string, that language is not at all called the empty language. Okay, so if no member in the language, then only the language is called as the empty language and denoted by null. Okay, the next definition with respect to that membership problem, given the string W belongs to sigma closure. The W is nothing but a string. W is belongs to epsilon closure. Okay, and the question is whether that W is present in language or not. That is the membership problem. Okay, you can have any W. Okay, that belongs to the sigma closure. But the question is whether the W is belongs to epsilon or not. That is called as a membership problem. Okay, for example, if you have the alphabet 0 and 1. Okay, if the alphabet is 0 and 1, and 0 1 0 1 is definitely a string of sigma closure. Okay, sometimes we can check whether 0101 is a member of the language which is formed by the strings of equal number of zeros and ones. So here the constraint of the language is the language consists of strings of equal number of zeros and ones. Okay, and you check whether 0101 has the equal number of 0 and 1. Yes, so it is the member of the language which is formed by the string of equal number of zeros and ones. Is it clear? Okay, now we shall see some problems related to that. Okay, so here some problems are asked in the gate questions. Okay, I can take a mixture of the problems because when directly I'm taking all the gate question, so it may leads to complex to you. So I'm taking the complexity level in a step-by-step way. So we start from the simple and get into the complex on for forming the language. Okay, so the first example, the language of odd length of strings of zeros and ones over 0 and 1. Is it clear to you? Is the question is clear to you? Kindly write down the question, the first question. You have to frame the language of odd length of strings of zeros and ones over sigma equal to 0 and 1. Kindly note down this question and we are going to produce the answer for that. Is it clear? What is language? Anyone? What is language? What is language? Anyone? Have you noted down this first one? Let us get into the answer for that soon. Here I will give you how to produce the answer for this. Let us take. This is the solution for the problem 1. Okay. The problem is we have to produce the strings of zeros and ones, okay, which is in odd length. That is called as the language here. Language is nothing but a set of strings. Okay. So first we have to write what are the odd length. Odd length are 1, 3, 5, 7, 9, 11. Likewise, it goes. It is in an infinite manner. Okay. Odd length is infinite. So in the string here is, symbol here is 0 and 1. So in length 1, what are all the strings we can produce? 0 and 1 alone we can produce in length 1. Okay, you know how many strings can be produced in length 1? Okay, as with the help of the previous formula, there are 2 symbols and in length 1 we are producing the string. So 2 power 1, totally 2 strings can be produced. Very similarly, in length 3, how many strings we can produce? 8 strings we can produce. Okay, how 8 strings? There are 2 input symbol and here the length is 3. 2 power 3 is equal to 8. There are 8 strings can be produced. They are 001, 00, 010, 011, the combination of zeros and ones. In length 5, we can produce a string. Length 7, likewise it goes because it is an infinite. By combining all these things together, we called that is the language, because language is the strings of odd length string. Here, all the member has the odd length. Okay, 0 is in the length 1, 1 is in length 1, 0, 0, 0 is in length 3. Likewise, all the member has the odd length. Is it clear? Is it clear? Is it clear to you? Kindly open your mic and tell. Do not chat. Is it clear to you? Shall I move on to the next problem? Any doubt? Any doubts? The text which is highlighted in blue color is the answer for the question. Any doubts? I move into the next problem, the second problem. Language of strings of equal number of zeros and ones. You have to write the language of strings of equal number of zeros and ones over sigma equal to 0, 1. Here also the input is 0 and 1. Okay, but the language consists of strings of equal number of zeros and ones. Okay, equal number of zero. First, possible number of zeros you have to write. Possible number of ones you have to write. Possible number of zeros are 0, 1, 2, 3, 4, 5, 6 and it goes up to infinite. Possible number of ones are 0, 1, 2, 3, 4, 5 and it also goes to infinite. The length of the string, equal number of zeros and ones. Okay, if there is 0 amount of 0, there is a 0 amount of 1. So this 0 plus 0 is equal to 0. That is the actual length of the string. Similarly, if one amount of 0 in the string, that should be again one amount of 1 in the string. So 1 plus 1, the length of the string is 2. Okay, if there is 2 number of 2 zeros and 2 number of 1, then the actual length of the string is 4. So the length of the strings present in the language is 0, 2, 4, 6, 8, likewise it goes. Okay, so now we have to write the strings in length 0. What are the strings in length 0? Only one string, that is epsilon, we can write. Similarly, strings in length 2. We know what are all the strings in length 2 for the zeros and 1 combination. 0, 0, 0, 1, 1, 0, 1, 1. But here one condition you have to make, the number of zeros and number of 1 should be equal. Okay, that condition we have to follow. If you take the first string 0, 0, I strike out this 0, 0. Why means this 0, 0, there is only 0 is there. There is no 1. So it should not be a member of the given language. I strike out this. 0, 1. So in 0, 1, there is a one amount of 0, one amount of 1. Equal number of 0 and 1 is there. I can take, this is the member of the language. And 1, 0, here also one amount of 1 and 0 amount of 1 is there. I can take, this is the member. And 1, 1, I cannot take. Okay, because there is no 0 is there. I can strike out this. String in length 4. How many strings I can write in length 4? 16 strings. Why 16? There are two input symbols, zeros and 1. 2 power 4 is 16. So 16 combination of zeros and 1 I can write here. And every length 4 string, I have to check the membership. Why membership? Because there is a constraint is given in the language. The language should consist of equal number of zeros and 1. If I take the first string 0, 0, 0, 4, 0 is there. But there is no 1. Condition is equal number of 0 and 1 should be there. So I can strike out this. The second member, 3 zeros and 1, only 1, 1. There is no equal number of zeros and 1s. I strike out this. 0, 0, 1, 0. 3 zeros and 1, 1. That is not eligible. So I can strike out this. Fourth string, 0, 0, 1, 1. There is 2, 0, 2, 1 is there. This is a valid string. I can take. This is the member of the language. The next one, 0, 1, 0, 0. I strike out this because there are 3 zeros and 1, 1 is there. Condition is equal number of zeros and equal number of 1 should be. Okay, the next member, 0, 1, 0, 1. There is 2, 0, 2, 1 is there. Okay, so equal. So I can have. This is the member of the language. Next, 0, 1, 1, 0, 2, 0, 2, 1. I can have. This is the member. The next is not at all a member because only 1, 0, 3, 1 is there. Unequal number of zeros and ones. The condition should be equal number of zeros and 1. Likewise, every string of length 4 is checked for the membership value. Okay, the strings which cannot be the member is striked out. Remaining thing can be kept under as a result. Okay, finally the result in length 0 we can have epsilon. In length 2, okay, except the striked out, the remaining thing 0, 1, 1, 0 can be brought here. And in length 4 also, except the striked one, the remaining things can be brought into the result. Okay, so likewise, length 4 only I can write. Length 6 is also possible. Length 8 is also possible. Likewise, it goes. So it is an infinite set. Okay, can you understand how this language can be framed? Can you understand how the language can be framed? Have you copied? Anyone?
2 minutes, ma'am.
Okay. At least you understand how I derive this result. Have you copied?
Yes, ma'am.
Okay. So let us go into the next problem. Now you have to tell me how the answers can be produced. So this is the problem. You have to produce the language of strings of 0 power n, 1 power n, where n greater than or equal to 0 over sigma equal to 0, comma 1. How we can make the solution of this? So this is the question. Is it clear? Now you have to tell me how the language can be produced. The language is 0 power n, 1 power n, where n greater than or equal to 0. So what is the first member of the language? What is the first member of the language? What is the first member? N starts from 0. First you write the value of n. N is equal to small n. N is equal to, start from 0. Greater than or equal to 0 means 0, 1, 2, 3. Likewise it goes. Okay. Whenever n value is infinite, definitely the L is also infinite. Okay. L is nothing but 0 power n, 1 power n. So 0 power n, 1 power n means first n value is equal to 0. So 0 power 0, 1 power 0. Zero power 0, 1 power 0. The next one, 0 power 1, 1 power 1. 0 power 2, 1 power 2. This one, this one. Zero power 2, 1 power 2. 0 power 3, 1 power 3. Okay, likewise it goes. Is it clear to you? Now you have to tell me what is 0 power 0, 0, 1 power 0. What is 0 power 0, 1 power 0? Anything power 0 is what? Anything power 0 is what?
1, ma'am.
It's not a mathematical power. It's a power of an alphabet.
Epsilon, ma'am.
Very good. Epsilon. Okay, anything power 0 here is epsilon. Okay, come on. Next, 0 power 1, 1 power 1. What is the resultant string you are getting? Here power means how many times the respective symbol is repeated. 0 power 1. It means what?
0, 1. 0,
0,
1.
1. Very good. Yes, 0, 1. Next.
0, 0, 1, 1, 1, 0, 1.
Very good. 0, 0, 1, 1. Next. 0, 0, 0, 1, 1, 1. Okay. Likewise, it goes. It is a infinite. This is the result of the line. Very good. Once you get clear about it, it is very easy to design the machine. Is it clear? At least this principle. Is it clear?
Yes, ma'am.
Let us see some problems regarding this language design. Have you copied this? First, you are writing the value of possible n in an increasing order. Then L as a pattern of 0 power n, 1 power n, you are substituting the n possible n value in every pattern and you are expanding it. That's all about the language. Shall I move on to the next? So now we are getting to what is finite automata. This is a very basic mathematical model. Why means because it has a inferior power when compared to push-down automata and Turing machine. But the real-time application of finite automata is very large. Okay, it has solved only the limited problem because of its no memory. Okay, it has no memory at all. Only it has a CPU and program memory. CPU and program memory is configured by state and transitions. Okay, and the finite automata is the simplest machine to recognize any pattern. So whatever, for example, in your ATM, if you are typing some PIN number, okay, that is called as the patterns. So such patterns are recognized by the finite automata actually. Okay, so that is the concept behind how you are validating your PIN number in a ATM. Okay, and this is the formal definition of the finite automata that is called as a mission. So it is denoted by the letter M, and which has the 5 components in it. They are Q, sigma, del, small q, F. This Q is called as the finite set of states. Okay, because you know the CPU and memory is configured by states and transition. States are circled. Okay, finite set of state is Q, and sigma is set of input symbols. Del is the transition. Okay, and Q, small q is the initial state. Why the initial state is denoted by the small q? Because it is a single state. Okay, capital Q is a set of state. The set is normally denoted by a uppercase letter, and the member of the set is denoted by a lowercase. And F is called as a set of final states because every finite automata may have more than one final state. So we called this is a set of final states. So these are all the 5 components of the mission. Okay. So even though it is not explicitly given, you have to understand these are all the 5 components of the finite automata mission. Q, sigma, del, small q, F, where Q is the set of states, sigma is the input alphabet, you know, and del is the transition function, small q is the initial state, and F is the set of final states. Okay. And there are 2 types of finite automata. One is called as the deterministic finite automata, which is abbreviated as DFA, and other finite automata called as the non-deterministic finite automata, which is abbreviated as NFA. Okay, so these are all the abbreviations for DFA and NFA, deterministic and non-deterministic. Okay, deterministic finite automata is DFA and non-deterministic finite automata is NFA. Again, in non-deterministic finite automata, we have the 2 forms of non-deterministic finite automata. One is accepting epsilon transition and the other is not accepting epsilon transition. Okay, so we have 2 forms of NFA with epsilon transition, NFA without epsilon transition. We shall see that in later. And DFA, okay, deterministic finite automata, okay, very similar to the general finite automata, which has 5 components: Q, sigma, del, Q, and F. all the different forms of finite automata is differentiated with the help of this transition function. Okay, I'm highlighting this transition function by red color. Why means because of this transition alone, the DFA and NFA is getting differentiated. Okay, transition is the function. So if it is a function, definitely it receives the arguments and return the value. The arguments for this transition functions are state and the input symbol. So we denoted that as Q cross sigma. Q is nothing but any state and sigma is the input symbol. So which receives two element as the argument. They are state and input. On receiving the state and input, it will give a state as the result. State as the result. So the result is gives Q. It is denoted as Q. Okay. You see this transition function, Q cross sigma leads to Q. Okay. Q cross sigma leads to Q means it receives two arguments, state and input symbol, and gives state. Okay. And deterministic finite automata, there are some interesting about the deterministic finite automata. For any input symbol, okay, the machine goes to only one state from a state. Okay, so the output is very deterministic. So we called this is the deterministic finite automata. All the real life application, the implementation of finite automata is a deterministic way only. We cannot implement non-deterministic finite automata. Okay, so once from any state, the output is deterministic, we can go with that. Okay, so deterministic finite automata is implementable in practical applications, and the transition function is defined for every state on every input symbol. And in DFA there is no epsilon transition. Okay, the epsilon transition is not at all allowed in DFA. Epsilon transition can be allowed in NFA, but it is not allowed in DFA. Okay, by reading the input symbol only, it can go from one state to other state. Without reading the input, it cannot go from one state to another. Okay, did you understand? Okay, so this is one example diagram of deterministic finite automata, which has two states, 0 and 1, and 0 is marked as the initial, okay, because it is pointed by a arrow. Okay, and one is called as a double circle, and one is denoted by a double circle. So whichever the states denoted by a double circle is called as a final states. Whichever the state denoted by a double circle is called as a final state. Okay, and there are the transitions. The transitions are denoted by a directed edge. From 0 state to 1 state, there is a 0 transition. From 0 state to itself, there is a 1 transition. From 1 state to itself, there is a 0 transition. From 1 state to 0, there is a 1 transition. Did you understand? These are all the possible transition in this DFA. Did you understand this? How the DFA is represented? Can you understand? This is the diagrammatic way of representing the DFA. The same DFA can be represented by means of one more representation that is called as a table representation. Okay, I can copy the diagram of this DFA here. Sorry. So this is the diagram of DFA. The same diagram can be represented by means of a table also. The table is nothing but which has some rows and column. The rows are representing the states and column representing the input symbol. States, the input symbols are 0 and 1. Okay, there are two states, the state 0 and state 1. There are two states in the diagram. The circles are called as the states. Okay, from 0 to, okay, 0 transition, going to where? 1. From the state 0 to 1 transition goes to itself. You understand? From 1, state number 1 to 0, it goes to itself. From state number 1 to 0, it goes to 0. Is it clear? Is it clear, the table representation? So in table, you have to mark this is the initial state. The state which is designated by an arrow is called as the initial state. Okay. The state in between, before there is a star sign, is called as a final state. Because in diagram, the double circle representing the final state, but in table, the state name which is preceded by the star is called as a double circle. Is it clear? This is the table representation. So there is a row on every particular state and there is a column for each input symbol. Okay. So the DFA can be not only DFA in NFA. All the finite automata is represented by means of either the diagram or the table. Is it clear? Is it clear to you? Is it clear about the representation? Yes or no?
No, ma'am.
Nova. Yes or no?
One more time, சொல்லுங்க ma'am.
The DFA, the any finite automata. Okay, what is a finite automata which has state and transition? Is it clear? At least that is
Yes,
clear.
ma'am.
States and transition.
Yes,
How the state is represented by means of a circle. The transitions are represented by a directed edge. Did you understand? So according to this diagram, is the diagram is visible to you?
Yes, ma'am.
Yes. How many circle in that?
2.
2. Okay.
2,
The
ma'am.
circles are named as 0 and 1. So there are 2 states in the DFA. Did you understand? Okay. The circle which is double circled is called as a final state. Final states are double circled. How many circle are double circled? How many circles are double circled?
1, ma'am. 1 circle.
Only 1. So 1, that is called as a final state. An initial state is indicated by an arrow sign. Even any indication is not there, by default, the first state is the initial state. Accordingly, the 0 is the initial state and 1 is the final state. And there is a transition. Transitions are defined by input symbols. Okay. So the directed edge, which has the label over it, the labels are called as the input symbol. So here there are 4 directed edge. What are they? 0 to 0, there is a self loop on 1. 0 to 1, there is a transition on 0. 1 to 1, there is a transition of 0. 1 to 0, there is a transition over 1. Isn't it or not?
Yes, ma'am.
Okay, these are called as the transitions. Okay, the transitions are defined by input symbol. What is the label of the input symbol? Again, 0 and 1. Did you understand? So the state name, I can call this Q0 for your differentiation. This is Q1. Okay, Q0 and Q1 I am having for state name. Okay, so from Q0 to 0, it goes to where? Q1. You assume that the name inside the circles are Q0 and Q1. Okay, so in order to differentiate the state name and the input symbol, you can have a name for the status Q0 and Q1. So Q0 to 0, it goes to Q1. See the directed arrow from Q0 to Q1, it is directed. Okay, and Q0 to Q1, Q0 to 1, where it going? Q0. Q1 to 0 goes to Q1. Q1 to 1, it goes to Q0. Is it clear now? Okay. I'm putting arrow in front of Q0. Why? Because it is the initial state. I'm putting star in front of Q1. Why? Because it is a final state. This final states are designated by a star sign in front of the Q1. Is it clear?
Yes, ma'am. Clear.
There are 2 representations. And another finite automata is a non-deterministic finite automata, which is called as the NFA. In NFA, epsilon transition is allowed. Okay. And similarly, from a state, there may be more than one outgoing transition is possible. Okay. For any input symbol. Do you understand? Okay. But these features may not add any power to the NFA. Okay. If you compare the NFA and DFA in terms of power, both are equivalent. NFA and DFA both has equal power. Okay, even though we are giving some relaxation to NFA, okay, the NFA is not have more power than DFA. Both are is in equal power. Okay, and one more thing, the DFA can be practically implemented. NFA won't be practically implemented because of this relaxation. If you are putting this relaxation to the machine, then the machine can confuse automatically. As a human, we can differentiate. Okay, by reading the input symbol in what path we follow, but the machine get confused. So the non-deterministic finite automata cannot be implemented. Okay, the non-deterministic automata, these are the 2 relaxation. I'm highlighted in blue color font. That is, the epsilon transition is allowed and there is a possibility of making the transition from one state to another on any number of times the particular input symbol. If you see the diagram of DFA, from 0, the 0 outgoing is going to only one state. If you see the table, you can understand very clear. The result of the transition, okay, I'm highlighting this result of the transition by yellow color, then you can understand. The result of the transition. The result of the transition is clear to you? I'm highlighting this by yellow color. The result of the transition. From Q0 to 0, it goes to Q1. Q0 to 1, it goes to Q0. Q1 to 0, it goes to Q1. Q1 to 1, it goes to Q0. Deterministically, there is the output. Okay? Only one output is there. That is a deterministic output. Did you understand? From a state, a single symbol going to only one state. Did you understand? That is a deterministic. Okay? But in case of the non-deterministic, it is not a case. Okay, for example, this is the non-deterministic diagram. Okay, I can represent this by means of the table, then you can understand very clear. Copy the diagram here. Okay, so this is actually the diagram. Okay, this diagram again can be represented by means of table. Very similar to the DFA. Again, we have the state. Here also the input symbols are zeros and ones. You see, the symbols are zeros and ones. Okay, we have the state name Q0 and Q1. Okay, in order to avoid the confusion, because the input symbol is also having the name 0 and 1. So see how the transition is going in this NFA. From Q0, the 0 transition goes to where? You tell me. 0 transition is going to Q0 and Q1. Isn't it or not? There are two output for 0 from Q0. Okay, you assume that the circle 0 is called as a Q0. Circle 1 is called as a Q1. Okay. From Q0, the 0 goes to both Q0 and Q1. From Q0, the 1 goes to Q0. From Q1, there is no outgoing transition for 0 as well as 1. There is no outgoing transition. Okay, is it clear? Is it clear how I am mapping the diagram into a table?
Yes, ma'am. Understood.
Okay. Now you see the difference between this NFA and DFA with the help of the table. In table, you see the entry. Here, from Q0 to 0, it goes to where? Q0 to 0, it goes to where?
Q0.
Q0 and Q1. There are two output. But in case of DFA, there is a single output for each cell. This consists of a single state only. Did you understand? So there is a deterministic output. Here, the output is not deterministic. You are directing the machine that from Q0, after reading 0, you are giving the path that the output may goes to either Q0 or Q1. If you are giving the output like that, the machine gets confused after reading 0 where it goes. Did you understand? The output is here is not deterministic. So this kind of finite automata is called as a non-deterministic finite automata. Is it clear? And some important points with respect to the finite automata. Every DFA is NFA, but not vice versa. This point is very important with respect to the gate. Okay, this question is frequently asked. Okay, is every DFA is NFA? Yes, every DFA is NFA. Is every NFA is DFA? No. Okay, that is the answer. And both NFA and DFA have same power. Okay, and each NFA can be translated into DFA. NFA can be translated into DFA. Did you understand that? Okay, so there is one question in gate. Okay, whether NFA and DFA has equal power or NFA has more power than DFA. What is your answer? That is a question in gate. Is NFA and DFA has same power or NFA has more power than DFA? What is your answer? The answer is NFA and DFA has same power. The NFA has not have more power than the DFA. Is it clear? Okay. And there are some multiple final state both in DFA and NFA. NFA is mostly for theoretical purpose. We can have the discussion about the NFA, but for practical purpose, the DFA can be used. Okay. So this is how the NFA and DFA can be represented in the table. This is about the extension of the DFA. The extension is nothing but how the DFA can be used to recognize the string. Because from the diagram and table, we are having the table how the state can be used to recognize the symbol. Because we have the column for the symbol alone, 0, 1, likewise. Okay. So we should have the column for string. We cannot have. So we have to extend the power of the DFA in order to accept the string. This is very important because we have to design the mission for accepting the language. What is language? Language is a kind of set of strings. Language is a kind of set of strings. So we should facilitate how the finite automata can accepting the string. Then only we can say how the finite automata accepting the language. You understand? The extended transition function of del is called as a del star or del cap. Any symbol can be used. So in del star, the second argument is different. Normally in del, you know what is the second argument of the del. Here I am highlighting. The second argument here is a sigma, that is the input alphabet. But in the extended transition function, the second argument is a sigma star because it is a string. In extended transition function, the second argument is a sigma star. Okay, so this is the formal definition of the extended transition function. That is how the DFA recognize the empty string. Similarly, how the DFA can recognize any length string X. You understand? Okay. So the first definition says, if the empty string is an argument, okay, del star of q comma epsilon is equal to q. It means by reading empty string, okay, the DFA cannot move from one state to another. Cannot move. It cannot move. But by reading the any length string X, the X may be any length. It may be n length. Okay. Then del star of q comma Ax is expanded as del star of q comma w comma e. That is, in order to recognize length n string, the length n string is split into two substring, length n minus 1 and 1. Okay. And every time it read one symbol, likewise it goes until it read a n symbol string. Okay. That is, it goes step by step. By reading one symbols in a string, it read completely the whole string. That is the meaning of the second one. Okay. It can move by reading a single symbol. It can move step by step. You understand that? Okay. For example, consider this is the DFA. Okay. The DFA has 4 states, Q0, Q1, Q2, and Q3. I want to check whether the string 0110 is accepted by this DFA or not. How can we say the string is accepted by DFA means, okay, by reading the string, if the DFA is reaching the final state. By reading the string, if the DFA is reaching the final state, then we can say the string is accepted by the DFA, okay. So you start the process from the initial state, okay. You see how I am doing the process. Okay, I start the process from where? Q0, initial state. Okay, see the below. Q0 I am starting. Okay, what is the first symbol of my string? The string given is 0110. Okay, the first symbol of string is 0. By reading 0, where I am going? From Q0, the 0 goes to Q1. So I stand in the state Q1. From there, I have to read the symbol 1. Okay, from Q1, by reading 1, where I am going? Q2. From Q2, by reading the third symbol 1, where I am going? Again in the state Q1. From Q1, I have to read the fourth symbol 0. From Q1, the 0 goes to Q0. I consume all my input. All 4 symbol I have read. Finally, I end up with Q0. What is the category of this Q0 state? Whether it is a final state? Whether it is a final state, Q0? I said the final states are double circled. Yes.
Q0 is final state.
Yes, very good. We stopped at the final state. Whenever we stopped at the final state after consuming of all the input, we say the given string is valid. Is it okay? The given string is recognized by the DFA. Is it okay? So, in order to recognize the string, how we are processing? We process the string step by step. Okay. By reading a single symbol, okay, we have to end up with the string. And finally, we have to check where we are end up with. If you are end up with the final state, we say the string is accepted. That's all. Okay, this is the acceptability. Okay, so the next class we shall see how the DFA can be designed from the set of languages. Okay, is there any clarification? I stopped here with. Is there any clarification as of now? Is there any clarification as of now? Rainul ma'am?
Yes, ma'am. Ma'am, HOD ma'am will be joining, ma'am.
Good evening, ma'am.
Ma'am, HOD ma'am will be joining, ma'am. 1 minute, ma'am.
Yes, yes, ma'am. Yes, ma'am.
Ma'am,
Yes.
next class unda ma'am.
Yes, yes, pa.
Ma'am,
Either tomorrow or Monday.
ஓகே மேம். அந்த நெக்ஸ்ட் கிளாஸ்ல வந்து கொஞ்சம் லாஜிக் சொல்லும்போது கொஞ்சம் தமிழ்ல சொல்லுங்க மேம்.
Okay, okay, okay. Definitely.
ஏன்னா லாஜிக் புரிஞ்சாதான் மேம் எங்களால பண்ண முடியும்.
Definitely, definitely. So these are all the basics because I can have the sample gate question here.
Okay ma'am.
So with respect to this language, you see this A comma B, A plus B, the whole closure star, without knowing, without having the understanding of what is the language, how the closure is operated, you cannot answer this. Okay.
Okay ma'am. Okay.
So is the classes clear to you?
Yes ma'am. Clear. It's very useful to you for me.
Very good. Thank you. Thank you, pa. Any other feedback? Any other feedback in what way I have to improve upon myself?
Yeah, good evening, ma'am. This is Sublakshmi here.
Good evening, ma'am.
Yeah, good evening, ma'am.
Good evening, ma'am.
Sorry, I couldn't connect you at the beginning of the session. I had an important phone call.
So not at all a problem, ma'am. Not at all a problem.
Nice having you for the session, ma'am.
Thank you very much, ma'am. Thank you. Thank you for your invitation and thank you for considering me for taking the class, ma'am.
Sure.
So you ask the feedback from the students, ma'am. If anything improve upon from my side, definitely I will be doing that, ma'am.
No, ma'am. I think the session has gone good, and I think the students are cleared. And for any other kind of feedbacks, I shall collect from the students and let you know for the further classes, ma'am. Thank you so much for accepting our invitation and
thank you,
having cleared the students with the concepts.
Thank you very much, ma'am.
Thank you on behalf of Department of IT and Fxec, ma'am.
Thank you very much, ma'am. Thank you.
Thank you.
So thank you, ma'am. Thank you, students. Thank you for your participation. So I expect your cooperation and all. In between, whatever the question is asked, kindly interact with me. Then only I can know at what level you are understanding the concept, because this is very, very important. This is not at all a theory paper. You have to apply your logic and all. Okay. So the aptitude is very important here with. So you have to interact me at any point of time. You can interrupt me. Okay. So even though you are saying the wrong answer, there is not at all a problem, because you are attending the class within your institute one. Okay, no other institute is attending the class here with. Okay, so without any hesitation, you can say your answer and you can clarify your doubts. Okay, so thank you very much for attending. I can stop sharing here with. Thank you, Zainul ma'am, for giving me the opportunity.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Please keep your front screen, ma'am. I'll take screenshot.
One second, ma'am.
Fatima ma'am, I think we can stop the recording. I think.
Yes, ma'am. Yes, ma'am.